For this week, we want to focus on the remaining Verilog operators, detailing what the operators are and how they function. And following that, we take a look at more complex expressions that use both self-determined and context-determined operators, and we look at the rules involved when we combine both self-determined and context-determined operators. Continuing our look at operators, we now look at the equality and inequality operators. The equality operator is the same as that in C. It's two equal to symbols, and the inequality is also the same. The exclamation mark followed by the equal to symbol. These are binary operators in that they take two operands and compare the two values. The output is always a single bit value, and it's always unsigned. If the two values that are compared are equal, the output is a 1. If the values are not equal to each other, the output is a 0. It is possible that we can have ambiguous comparisons. And let's see an example of what we mean by ambiguous comparisons. In this example, the 3-bit value for A is x11 and the 3-bit value for B is 011. When these two values are compared, the output is x. The reason for this is that equality depends on this bit here. If this bit was a 0, the two values are equal, and if this bit is a 1, the two values are not equal. This comparison is considered an ambiguous comparison. If we take another example, this time with the value 001 for B, then when the two values are compared, the output here is 0. And the reason for this is that no matter what value we have for x, the two values can never be equal. So this is considered an unambiguous comparison, even though we have an x bit within one of our operands. So the two values we've got here can never be equal, no matter what the value for the x bit is. The equality and inequality operators are self-determined operators. This means that the size of the operands are only determined by each other and not anything else. And this makes sense as the result is just a single bit. In the case of one operand being shorter than the other, the same rule applies as that used for the relational operators. There are two additional operators in this group. These are known as the literal equivalence operator and the literal inequality operator. They can also be referred to as the case equality and case inequality operator. Taking an example with the literal equivalence operator, the way in which it works is that when two values are compared, the output is a 1 when the bits match exactly. So what this means is that in the case of having something like this, we only have a match if the bits match exactly. So let's go through it. The first bit here matches with this bit, that's okay. The second bit matches with this bit, that's okay. And our third bit does not match exactly with this bit. So the output is a 0. The only way in which we get a 1 at the output is if we have an x here. And in this case, we have an exact match for all 3 bits. In general, the literal equivalence and literal inequality operators are useful for debugging and in test benches. And for the moment, we do not need to concern ourselves with these operators. And when comparisons are needed, you can use either the equality or the inequality operator. Our next group of operators is the bitwise operators. And the operators in this group include the AND operator, OR, negation, exclusive OR, and the exclusive NOR. There are 2 operators for the exclusive NOR. The bitwise operators perform bit-by-bit operation on 2 operands. So for example, if we've got A ANDed with B, and let's say A and B are both 3-bit values, the bitwise AND is performed as follows. Corresponding bits are ANDed. 1 ANDed with 1 is 1. The next 2 corresponding bits are ANDed. 1 ANDed with 1 is 1. And the last 2 corresponding bits are ANDed. 1 ANDed with 0 is 0. The bitwise negation operator is a unary operator. That means it just operates on one operand. To use the bitwise negate operator, we'd have something like this. Negate A. If A has the value 0, 1, 0, the result of this operation is to negate all bits. And the result is 1, 0, 1. These operators are context determined, meaning the size of the result will depend on other sizes within the expression, as will the size of the operands also depend on other sizes. As an example, let's take the logical AND operator. So the size of the result will depend on other parts of the expression. But in the simple case where we just have A ANDed with B and nothing else, the result will be a 3-bit result. As to whether the result is signed or unsigned will depend on the context. So in our simple example, if A is signed and B is signed, the result is signed. There's one subtle point with these operators that relate to bit extensions. If, for example, we had a 2-bit value for B, that value must be extended, in our example, to 3 bits. For the bitwise operators, this is always an unsigned extension or a 0 extension. In this example, our result is a signed quantity, but for the bitwise operators, bit extensions are always unsigned, meaning we insert zeros into the additional bits. As noted, the negation operator is a unary operator, so it only has one operand. And in our simple example, the output will be 3 bits, but may be different depending on the context for more complex expressions. We've seen these tables earlier in the module, and these define the operations for the bitwise operators. Let's see some examples of using the bitwise operators. If we want to model this logic, we can do so as follows. Here we're ANDing A with select. Here we're ANDing B with the inverse of select. And we're ORing those two results. So we've got the bitwise AND, bitwise AND, the negate, and the OR operators. The use of brackets makes it easy for us to read the expression, and it also ensures that the operations perform in the order that we want. If we look at the precedence table, we'll see that the bitwise AND has a higher precedence than the bitwise OR, and the negation operator has the highest precedence. We could actually have written the expression as follows. And we'd have achieved the same functionality. But if you're in doubt about the precedence of any of the operators, it's best to use brackets to ensure that the operators are performed in the order that you require. Let's take another example. Let's say we want to implement the following functionality. In this example, we have 3 vectors, A, B, and C. Each is an 8-bit vector. And we want to implement the following functionality to obtain D, an 8-bit vector. Because we are performing the same bitwise operations on each group of bits, we can model this operation as follows. So A is ANDed with B, and the result is then exclusive ORed with C. So what we're doing here is we're ANDing the 8 bits of A with the 8 bits of B. That's providing us with these values here. And then we're exclusive ORing those values with C to provide our outputs. If you look at the precedence table, you'll see that the exclusive OR operation has a lower precedence than the AND operation. So we could actually omit our brackets and have the following: A ANDed with B, exclusive ORed with C. And from the precedence table, we know that the AND will occur before the exclusive OR. But I recommend you use brackets. It makes the code more readable and avoids any mistakes in misinterpreting precedence rules.